Hello, so today we are going to look at this problem called delete a node in a binary search tree. And the problem consists of deleting a node with a given key in a binary search tree. And so we get a binary search tree as an input and the key, and we want to return the root node of that binary search tree after we remove the node that has the same value as the key. And so, for example, here we have this tree that can be represented as an array this way and looks like this, really. So it's a binary search tree because the smaller element for each node are on its left and the bigger elements are on its right. And so with this binary search tree here, we want to remove the key. So with this one, for example, we want to remove the key 6, right? This key 6 here. So after we remove it, we take the left value, we put it in place of 6, and we mix the right value as the right node as the right node of the new parent, which is the left node. And so we end up with something like this, where this subtree here became 4, 7. So the other approach that we can do this is we could instead choose to replace the parent with the right node and make 7 instead of 6 and make 4 the left child of that and not have a right child. Okay, so this is one of the solutions. Okay, so let's see how we can solve this. So here is an example of a binary search tree where we have I have here a very large binary search tree so that we can illustrate with the multiple examples, right? So here you can see we have multiple cases, right? So the easiest case is if it's a leaf node, right? Actually, let's backtrack a little bit and first explain what a binary search tree is. So binary search tree, the main property is that you have a node and then you have its left and its right subtrees or right nodes. So the property of a binary search tree is that for every node, even nodes down the line here, we have the property that all those to the left of a node have values smaller than the node, and all those to the right have values bigger than the node. That's the main property here, and that's what we will need to maintain after we delete the node that has the key that we are looking for. And that will also help us search for the key value, right? Because we know that if it's smaller than the root node, going right won't give us anything, but we should go left because we know all those smaller than the root node, if they are in the tree, then they are on the left. And a similar thing, if the value is bigger, we have to look right, because if they are bigger, they won't be on the left, right? So that's the main property. Now let's try some examples here. So the simplest case is if the key value is equal to 1, for example, which is a leaf node. Then at that point, we don't need to do anything except to just delete 1, right? So that's an easy case. Now the tricky case becomes when, let's say, it's in the center of the tree or it's the node itself. So let's take an example. If it's 14, then it's also kind of simpler, because if it's 14 like here, what we will need to do is just remove this node here, but then we'll need to replace, right? 10 needs to be linked to the other subtree here. And so what we can do is just make 10 here have as a right child 11. And that's pretty much it. So what this means is that, let's write down if. So here, the case that we had is that 14 didn't have any right subtree. So if node.right is none, then what we can do, I'm writing it in Python notation here, what we can do is just assign as the parent the root of the left subtree, right? That's what we did. The parent is now became 11. What I mean by the parent is the parent in this context, in this subtree, not the parent of the entire tree. So assign as the parent the root of the left subtree. And here, of course, node represents the node that has value key. So here, one thing we did here to look for 14, so 14 was here, right? So one thing we did to look for 14 is that we come to 20, we find that 14 is smaller, so we go left. and then we come to 10, we find that 14 is bigger, so that means we need to go right, and then we come here, we found it, and the node is now at 14, and that's why we look and it doesn't have any right node or any right subtree, and so we do this where we assign the parent as the root of the left subtree, which is 11 here, which is this orange link here. Okay, so let's take another example. Let's remove this and take another example. So what if the key was, instead of 14, what if it was 31? So if the key was 31, then in this case, first to look for the tree, we start out from the root node, which is 20 here. And we find that 31 is bigger than 20. That means we need to go to the right. And right away we find the value, so the node is here. And one property you can notice with this 31 is that we don't have any left subtree. So in this case, let's just write down what we will need to do. So if node.left is none, so this is of course when we find that node.value is equal to key. So at this point, what we need to do is we need to assign as the parent. So what we do here, if I just show it here, so let's remove this. So we will make 39 the parent. So what this means is that we remove this link, and now we have, basically we have this. So we assign as the parent the root of the right subtree. So a similar thing to what we did here. So we assign as the parent the root of the right subtree. So one thing here that I need to mention is that this is not really an explicit removal of these links that we'll be doing. We will just be using recursion and just return this node.right. And then by definition, the node would have said node.right is equal to whatever the recursive call will return to me. And then that would kind of link the root to be, the root right to be this one, to be 39, right? Okay, so this is the part where we find that the node is equal to key. Let's just write the part that we did where we were looking for the node, which of course would be at the beginning here. But I'm just going to write it here. So that would be, well, we are looking for the key, right? So we say if the key is smaller than the node d'avant, whichever node we are at, maybe the root, maybe the nodes after that, then we need to go left because it's on the left subtree. So at that point, what we can do is just say we need to go left and we need to delete there, which means that we need to just do a recursive call and assign that to the node.left. And so we do a recursive call here, let's call it delete node. We are going to look for it on the left, and then when we find it, we are going to delete it with this block that I just wrote here. So that would be look for it on the left and delete it. And of course, we'll pass the key. Now, if the key is bigger than the node d'avant, that means we need to look right. So to look right again, we just assign whatever the result that of the recursive call, and this is why when we find it at 31, and then we just return the node.right, then that would be linked to the root node.right. So to do that, we just take node.right and assign the result of delete node for node.right, and we pass the key. And that's pretty much so these are the cases here for when we are searching for the node, but there is one more case here when the node.val is equal to key, which I would apologies here for the very organized code. I will reorganize it later, but here when the node.val is equal to key, we can have this case where the node.right is none, the node.left side is none, or maybe both are not none, and then in that case we need to do something else, which is here if basically the node.val is equal to the key and we have both a left node and the right node, is not none basically, and also the node that right is not none. What shall we do? Let's take an example here. So when would that happen? So let's go to the original tree here. So let's say the key now is, let's say we have a key equal to 39, right? Instead, so now searching for it, which is this portion here, would mean that we will start at the root node, find 20, 39 is bigger, so we need to go right. So we go right, we go in this direction here. 39 is bigger than 31, we go right again, and we find it here, right? So once we find it, now we need to, it has both a left subtree and a right subtree, so we can't do these two conditions here. So we have to find something else. So what is the logical thing? So we need to maintain a binary search tree property, which means we need to remove 39, but still keep anything to the left of 31 to be smaller than it, and anything to the right tree bigger than it. So we need to keep that property. So here we have two choices actually. So let me just list these two. So we need to find, let's call this the successor of 31, because the successor was 39, but we want to delete that. So which one, 35, 47, 31, or 38? Which one should we make the parent or the successor of 31? So we have two choices here. One is we can take the smallest node on the right subtree and make it the parent. Or we can, the other choice we can do is make the largest node on the left subtree and make it the parent. Now, why do these two choices work? Let's first take in the smallest on the right subtree. So the smallest node on the right subtree, so what do we want? We want it to be, since it's on the right of the parent, we want it to be bigger than it. But since it's on the right of this node here that we will be deleting, it's by definition bigger than that node. So it's by definition bigger than 31. Right? So that checks out for the binary search tree on the right side. And it's on the right side, so it works out. What if we take one on the left? So still, those are smaller than 39, but because of the binary search tree property, they are already bigger than 31, so that still works out. So here that means that we can take either the smallest on the right, which means we have just 47, so we just assign 47 as the parent, or we can take the largest on the left, which means here we can take 38 and make that the parent. So if we make 38 the parent, we'll have a subtree like this, 31, link it to 38, and then 38 has a child 47, so this is case 2. And then we would have, so now that we put 38 here, what should we do? We should put, on the left, keep 35 and 31, but we should delete this 38, because we don't want to duplicate it, we put it as the parent, so we should delete this portion here. Now, what happens in the first case? So in applying the first case, what will happen is that, well, we will put 47, so we'd have 31, we'll have 47 as the parent, and then we'd have the left subtree, we will attach the left subtree as the left subtree of 47, and so we'd have 31 here, 38, but then this 47 also, we shouldn't duplicate it, so we remove it also, right? And so you can see in both cases, we still have the binary search tree property where the right of 31 is still bigger than it, the left subtree is still smaller than the node, and the right subtree is still either empty here or in the previous example, it was bigger, right? So here, let's just write down what we are doing here. Let's write down just using this first case. And then after that, we can do the second case. So for the first case, what we need to do is we need to find the smallest element on the right, and the smallest element on the right is just the leftmost element on the right subtree. So finding that, well, we need to first pick a node, and let's just call it the smallest right node, and it's at least the node.right value, right? In this case, since we have only one and it doesn't have a subtree, it's just that one. But if we had, let's say, a tree here, maybe with some values like this on the left, then the smallest value would be the one on the far left, right? Because whenever you go left, it's smaller. And so we need a while loop here to find the leftmost one. So we say while smallest right node has a left node, we keep going. And keeping going means basically just go to the left side more. So that would mean that smallest right node, that left, is equal to the node that is to the left of it. So that would mean is equal to the smallest right node, that left. And when we exit out of the while loop here, that means that we found one that doesn't have a left node, which means it's the leftmost one. So here now what we did is we put that value as the root, as the parent here. And so the parent is the node, right? Because that's where we found that the value is equal to the key and we want to delete it. So to do that, we just assign the smallest right node, make its value the node's value. So just assign its value to node.val. And that means in this case, when we had 39 here, we'll just put here 47 instead. But remember, the second step was to remove this 47 because otherwise we'll have it duplicated. And so how would we remove this? Well, our method function is called delete node. That's what it does. So let's just delete this 47, but delete it only starting from the right, right? Because we don't want to delete the node that we just put. So just delete it from the right subtree, and that by definition will just delete this 47 here. So to do that, we need to call delete node on the right subtree, so that would mean node.right. And what is the value that we want to delete? It's the value that we just put in the parent, and we want to remove it from the right. And so to do that, we just say node.val instead of the key, right? And so here, what should we do once we get that? That's what we should assign as the right subtree of this value here. So that would be node.right. Okay? And that's pretty much it. So this is the step when we have both left and right. So this is using the first case where we do the smallest on the right subtree and make it the parent. So the other choice that we can do here that isn't is instead of doing this in here, let's just say or, we are going to look for the largest on the left subtree and make it the parent and do a similar thing here where we delete the node so that we don't duplicate it. Let me just write down what we did so that we can use it here as a reference. So the leftmost, the rightmost, the largest one on the left side is the one the rightmost one, right? So that's 38 in this case here. So let's just write this down. So we would take 31 and instead we put 38. And the tree we had before had 35 here, and then had 31 and 38 that we want to remove. And here we still have 47. So what we want is want to remove this also. So first we need to find the largest left node, right? So largest left node. And so we start out on the left subtree, of course. So we start out from the node.left because we want to get to the largest on the left subtree. And while it has, and the largest on a tree is just the rightmost one, right? Because whenever you go right, the values increase. And so we want to say while largest left node right, because we are looking for the rightmost one. We do the same thing, we keep reassigning. So largest left node is equal to largest left node dot right. And then we do a similar thing here where we pick the values. So this was 39, we pick 38 and we put it in the value of that node. So what that means is that we say node.val is equal to the largest left node .val. Okay, and now we need to remove this 38 because now it's a duplicate here. So to do that, well, we just delete it from this left subtree. We just delete it from this left subtree and then assign this left subtree the result of the deletion from this left subtree to the left of 38. So how do we assign it to the left of 38? 38 is just node. So we assign to node.left the value of deleting the value that we just put in the node here, which is 38, which is the largest left node.val, which here right now it's in node.val. So we just delete that from the left subtree, so node.left, and we delete node.val. We could also just put largest left node.val, that's the same thing. And that's the second way of doing this one. And that's pretty much it. So we kind of have two things going on here. One is finding the position of the element or of the node that we want to remove, and then when we find it, we have three cases. Either it doesn't have a right subtree, and then we just assign as the parent the root of the left subtree, or it doesn't have a left subtree, and at that point we just assign the parent as the root of the right subtree. And if it's a leaf node, then it will just go into whichever one we put first. If we put this one, node.right is none, then it will just return the root of the left subtree, which is none, and that would be just removing the leaf node. So we don't need to handle that case, specifically the case of a leaf node, like the case where the key here is equal to 1. Now, if neither of these are true, then it must be that the node has both a left and a right subtree, and at that point we have two ways of handling this, and they both work fine. And so one of them is we assign, instead of we assign to the node that we want to delete, we replace it with the smallest right node, which means basically the leftmost node in the right subtree. Or we do the other method where we pick the largest on the left subtree, which basically means we assign the rightmost node on the left subtree. And then we, of course, delete that node because we don't want to duplicate it. And we delete it just from either the left subtree in the second method or from the right subtree in the first method. And we assign that as either the left or the right in each case, right? And that's pretty much it for this one. Now let's just talk about what's the time complexity here. So because it's a binary search tree, you see here when we are searching for the nodes, we either go left or we go right. We never go in both at the same time. And the same thing here, we either do this method or do the second method. And in each case, we either go left or right. We do one of the methods. This one just goes to the left. And so at most, in the worst case, we will go to the far left or go to the far right. And so that would mean at most we will do the height of the tree. So the time complexity here is just the height of the tree, if h was the height of the tree. And so our time complexity here is just O of h, and h here is the height of the tree, which is just log n, if n is the number of nodes in the binary search tree. In terms of space complexity, if you see here in our recursive function, it's a recursive function, so we are using some stack, right? So, and the number of recursive calls is the same as the time complexity because we will call the function at most the number of ways we go left or go right. And so there also the space is O of h. But if we convert this and do an iterative solution, we'll get to an O of 1 solution because the only space we are using here is the stack to do the recursive calls. Yeah, so that's it for this. So let's code this up and run it on some examples. Okay, so now let's write down the solution, that the first one that uses looking for the smallest right node. Okay, so the first thing is we are going to do here is the first part, which is looking for the node that has a value equal to the key. And so the first thing we need to do is, if the root node is empty, I'm just going to rename this node so that it works on the recursive calls, right? So if the node is null, right, so there is no need to go further, we can just return it. And either it's the key value, the node is just one node, and we can just return it, right? Sorry, return it. Or we are doing a recursive call and then we will return this to the caller, right? So now we will be looking for the key, and since this is a binary search tree, if the key is smaller than the node value, that means we should go left. And so going left means we need to call delete node on the left subtree and try to find it there. And whatever the result is, because it must be there if it exists, then we'll remove it from the left subtree, and the result of that we need to assign it to the left of this node after the deletion, right? Or it's not, and then maybe it's on the right subtree. And so at that point, we need to do the same thing for the right subtree. We need to delete it from the right subtree because it's bigger than the key. So the key is bigger, so it must be on the right. So we pass right here and we pass the key. Or it's equal. At that point here, the key is equal to node val, which means we found it. So we need to delete this node pretty much. And so deleting this node, as we said, we have three cases. Either we don't have a left subtree, and in that case here it doesn't have a left subtree, and at that point we can just make the parent be the root of the right subtree. So to do that, we can just return the root of the right subtree, which is just node.right, and make that because right now that means that the node is deleted, because now if the call was this one, the node.left will become the node.right here instead of it was the node itself, right? And otherwise we are in the second case, which is node doesn't have a right subtree. So we check that if node, not node.right, which means that node doesn't have a right subtree. And we do a similar thing where we just return as the parent the root of the left subtree, which is just node.left. Or in this case, it has both a left and a right subtree. So we are going to do the first method, which is pick the smallest right node, which means basically going to the right subtree and picking its leftmost node. So to do that, we just say we are looking for the smallest right node in the right subtree. So we start from node.right and we look for its leftmost node. And so to do that, we say while smallest right node has a left node, we keep going left. And so to do that, here we say this is equal to smallest right node.left. And when we are done here, smallest right node would have the value of the leftmost node on the right subtree. And so we want to make this here the parent. So we want to replace node.val with this, because this is what will be what will replace the node that we'll delete. And here, instead of deleting, like really just doing a delete, we'll just take the value and put it instead of the value of the node that we want to delete, essentially. So that would mean that node.val here will become the smallest right node value, and essentially overriding the node's value, which is the value that we want to delete. And now we have a problem where we have a duplication here, where we have the value here of the smallest right node is both in the node and in this node. So we want to delete it from this node here. And so to do that, we are going to, since it is on the right, because that's where we started from, we want to reassign the right subtree to be deleting this value from the right subtree. And the value is just node.val. We can also just use smallest right node val, both work fine, okay? And after that, we can just return the root, the node, because we will have updated it at this point. And that's pretty much all there is for this method. So let's just run it on an example here. So what we need to do first is just create the class. I have a tool here just shows us the tree. So let me just first show you what the tree looks like. So we would use this here to draw it. Okay, and then we'll delete it and see the result after. We'll delete the node at positions, the node of value 6. So the tree looks like this: 8, 7, 4. Sorry, not this here. Run it again. So the tree looks like this. We have 8 as the root. We have 6, 4, 7, 9, 10. So we want to remove 6. So in this method that I did, which is removing the smallest right node, basically replacing the node with the smallest right node. That means 6 will get replaced by 7. And so let's see if that works. So if I comment this part here, this part just draws the tree that deletes the node at position 7. Sorry, that deletes the node that has value 6. And so if I run this, yeah, we have. Okay, so actually I had a small error here where this should be returned here, because we want to return this node also for these two cases, right? So we'll return the node here at the end. Now let's run this. And the result is we deleted the 6 that was here, replaced it with the 7, and we have still the left subtree to be 4 here. And so this works in this case here. We can try other example. You can try other examples yourself if you want, but this should work fine. Now let's just do the second method, which is instead of picking the smallest, let's just comment this part here. Instead of picking the smallest right node, we will do the second method where we pick the largest left node. So to do that, we just say left. Largest left node is just the rightmost node in the left subtree. So here, largest left node. So we will start from the left because we are looking in the left subtree, and then we say while largest left node, that right, because we are looking for the rightmost one, that's the largest one. And we do a similar thing here where we reassign that to be the right node. Then when we exit the loop, that means that we found the rightmost node because there is no right element after it. And so here we want to make this the parent, so that means that we want to put in node.val the value of the largest left node. And then we do a similar thing here where we want to delete from the left subtree this value here so that we don't duplicate it. And so to do that, we say node.left. We want to delete node.right. Sorry, in node.left here. That's where we want to delete the element. And what will help us here is that we won't go into this case again because we know that this is the rightmost node in the left subtree, which means that it has no right subtree, which means we will fall in this case for sure. And then we will return this node.left immediately, right? And that's pretty much it for the second method. So let's just make sure that it also deletes 6. Fine. And so you can see here, now 4, which is the left node, took place of the parent and now took place of the 6, and it has now the right subtree to be 7. And so we still have the binary search property because 4 and 7 are still smaller than 8. 7 is bigger than 4, so it's good to be on its right. And 9 is bigger than 8, so it's still we still have binary search property, and the same thing for 10. And yeah, so that's pretty much it for deleting a node from a binary search tree. Thanks for watching, and see you on the next video.